Welcome. In this training, we will define data loading features in Snowflake and analyze their potential impact on performance and cost. Let's get started. To begin, let's define what we mean by data loading in Snowflake. Fundamentally, it is the process of ingesting data from external files or streams into your Snowflake tables. You have the flexibility to load from internal stages, which are managed within Snowflake, or external stages like S3 or Azure Blob Storage. The definition of your loading strategy relies on understanding the two key approaches: bulk loading, used for large historical datasets, and continuous loading for near real-time needs. Snowflake natively handles structured, semi-structured, and even unstructured data, removing the need for complex preprocessing. In this visual, we start with data sources on the left generating files. These files land in stage storage, which can be internal or external. From there, we branch into the load method. You can choose batch processing for bulk loads or stream for continuous ingestion. Both paths ultimately deposit data into the Snowflake table. Now, let's define the specific features of each method. Bulk loading utilizes the copy into command and relies on your user-managed virtual warehouses. This is your go-to for nightly ETL jobs. In contrast, Snowpipe is designed for continuous loading. It uses Snowflake-managed serverless compute to load data within minutes of file arrival, responding to event notifications. For even lower latency, Snowpipe streaming writes rows directly via API, bypassing files entirely. Your choice here directly impacts latency and how compute costs are categorized in your bill. Here we map the flow based on the method. Data files enter the decision point. If you choose bulk, the workload goes to a user-managed warehouse. If you choose Snowpipe, it routes to serverless compute. If you choose streaming, it bypasses file staging via API direct write. All three terminate at the target table. A critical feature to define is Snowflake's ability to transform data during the load. You don't always need an external ETL tool. With the copy into command, you can use select statements to reorder columns, cast data types, or truncate strings on the fly. We also have schema detection using infer schema to automatically figure out your file structure. Furthermore, schema evolution can automatically adapt your target table if the source data adds new columns, significantly reducing pipeline breakage and maintenance overhead. This chart explains the smart loading process. A raw file is analyzed by infer schema. We check if the schema matches the target. If no, the system triggers evolve schema to adjust the table. Once aligned, we transform data, applying casts or reordering before writing to the final table. Let's define the potential impact on your resources. For bulk loading, you are billed for the time your warehouse runs, so sizing it correctly matters. Snowpipe is billed based on actual compute usage plus a management overhead. A major impact factor is file size. Snowflake recommends files between 100 and 250 megabytes. Too many small files increase overhead and compilation time, while massive files prevent parallel processing. Also, remember that files sitting in stages incur storage costs, so purging them after loading is a best practice. This diagram analyzes the impact of file size. Input files undergo size analysis. If they are the optimal 100 to 250 MB, you achieve optimal parallelism and lowest cost per row. If they are too small, you get high overhead. If too large, low parallelism. Both suboptimal paths lead to increased cost. Defining how you handle semi-structured data is crucial. Snowflake supports formats like JSON and Parquet natively. You can load these directly into a variant column, preserving the hierarchy, or split them into separate columns during the load. The potential impact here is on query performance. While variant is efficient, flattening frequently queried fields into standard columns allows for better data pruning and faster results. Options like strip outer array give you fine-grained control over how arrays are parsed during ingestion. Here we see the strategy for semi-structured data. JSON or Parquet files arrive at the load strategy decision. You can load as raw into a variant column for a flexible schema, or flatten the data into relational columns to achieve faster pruning during queries. To summarize, define your loading strategy based on latency needs. Copy into for batch, Snowpipe for events. The potential impact on cost and speed can be optimized by compressing files and partitioning your stage paths logically. Always monitor your load history views to track credit consumption. Finally, define your error handling strategy using on-error options to ensure your data pipelines are robust and don't fail completely due to minor data quality issues. This summary flow starts with identifying latency needs. If you need low latency, choose Snowpipe. For high latency tolerance batch, choose copy into. Both paths require you to optimize files, size/compression, and monitor usage to finally achieve cost efficiency.